different coefficient expansion this time. We'll use the betas now. We'll be talking about delta V is V naught beta times delta T. This time, we want to know what temperature change would cause a 0.2% increase in the volume of a quantity of water that's initially at 20 degrees Celsius. You'll notice in the table that it gives you these thermal expansion coefficients for some materials at 20 degrees Celsius. That means at or around 20 degrees Celsius. If your initial temperature isn't exactly 20, what do we have on the last one? 28. We still use these coefficients in here, even though this says 20. It does not need to be exactly 20. This is for temperatures kind of in that range. Nothing for very extreme temperatures, very high or very low. These are all fine to be using for anything we're dealing with. You're not going to have to account for that being any different. Okay? In this problem, we give you the initial temperature of 20 degrees. We're not even going to need that number. It's just going to give you reference here that we're at a temperature that says we can use the table there for our coefficients of expansion. Okay. But we just want to know what temperature change must we have here to cause a 0.2% increase. In the volume of the water. So we can look up water there in our table to get the coefficient of expansion for water to be 2.1 times 10 to the minus 4. Okay. And what units does that have?
Degrees Celsius.
Degrees Celsius to the minus 1 there for that beta. So all we know is that's the amount of increase that we have. We know the initial temperature. We know our coefficient of expansion here. Well, how do we write this statement right here in terms of variables? We want a 0.2% increase in the volume of the water. How can we say that with an equation here? There's some variables that represent that 0.2% increase. I know you guys hate percentages, or some of you do. We've had these a few times in the last couple of weeks, I think. We find an increase of 0.2%.
It would be the initial plus 0.2 V, or
So,
plus the 0.2 initial, so I guess.
Yeah, so the initial, what I start with, the increase is 0.2% of that. Write the 0.2 as, or the point, yeah, the 0.2 as a decimal. So this would be 0.002 times V naught. This would be equal to your final. Take the amount of increase or decrease, add or subtract from the original. That's how you always get an increase or a decrease with percentages here. Okay. Always change your percentages here to a decimal. I know it's already a decimal of a percentage, but change that to a decimal and divide it by 100. That's how we get this. The common mistake here is that people forget this, and they just do this part right here. Remember, if it's an increase or a decrease, you're adding that on or subtracting it from the original. Okay? If I'm increasing my volume by 0.2%, then my final volume needs to be bigger than what I started with. And if I just wrote this, this is just simply telling me the amount that it increased by, not what my final volume is. So my V is equal to 1.002 V naught. That represents the 0.2% increase in the volume. Okay. Does that make sense for everybody? Do you ever calculate percentages in your lives at all, ever? For what kind of things? Tips? Sales? Yeah, and a lot of times people will calculate the percent, 20% off, and then subtract that from the original. What's another way to do that? If it's 20% off,
It's multiplied by 80%.
when you give a tip or you're paying sales tax, don't calculate the 8.5% and add that on, just multiply by 1.08 and that gives you the same thing. And that's where this one's coming from. We're always talking about an increase or a decrease. And that's why you have the one here. Okay. So when you're paying sales tax, I mean, a lot of times people will just plug in the sales tax, figure out what that amount is, then add it on. Not that it really saves you that much time, but if you're ever calculating it, I guess if you ever ran a store and you didn't have a cash register that did it for you, you really should be doing it this way with the one instead of the other way. And, well, then some stores might not have fancy machinery.
The world would end unless
The world will not end for me, because I can still do this stuff.
Yeah,
Now you're gonna know how to do this stuff
You're not
too.
running a store though.
Okay, so we've got our V as an expression here in terms of the initial. We can take the delta V, and what are we looking for here? The temperature change. So V minus V naught is equal to V naught beta delta T. Okay. Now, this equation, if we were thinking about this, gives me an equation here for the change in volume. The change in volume is just this part right here, 0.002. We could have just left that like that for the delta V if we didn't want to write out the V like this. We wrote it this way because I think this is the way we've been doing things, just to talk about a percent increase. Okay? But if now you think about it, if my equation has delta V in there, and delta V represents the change in volume, this is the amount that the volume changed. That was the amount of increase. So I could have just started off and let my delta V be 0.002. I'm going to write it out this way just because I think this would probably be more natural for most of you to write it out this way, and you'll see that we end up getting the same thing either way. Right? But if you look at this now, the final minus the initial, you get that 0.002 V naught. If you happen to have recognized that from the beginning, that is your delta V, you could have started here. But if we wrote it out like this, then you just need to expand out the delta V as we did. Okay? So the initial V's cancel out. We can solve this for the delta T by just dividing by that coefficient of expansion here, which we wrote down, and that is 2.1 times 10 to the minus 4. Degrees Celsius to the minus 1. And that Celsius to minus 1 gets flipped up to the top of the numerator there, and then we get our answer in degrees Celsius to be 9.52. Make sense over here? Okay. So we talked about expansion of fluids, of materials, due to forces, due to temperature. Let's start talking about gases now. The ideal gas law is something that most of you have used. PV is equal to nRT. I'm just going to write down all these things. And you all know, many of you know that P is pressure, V is volume, N is number of moles, R is a constant, and T is temperature. If you've been in chemistry, hopefully you remember that equation. Okay? So I'm going to put on here the units that we're going to be using for what we're going to do. Remember, this pressure, any P without a subscript is what kind of pressure? Which one? Which? Total or the absolute pressure? Remember, we had absolute pressure, we had gauge pressure, we had atmospheric pressure. Anything without those subscripts, these are always in absolute pressures here. I'm going to put the units here. This is in newtons per square meter. Okay. We have a V for volume, which should be in cubic meters. N is equal to number of moles. The problems that we're going to deal with won't have changes in the number of moles, so I'm not going to define what the moles are. We're not going to write down Avogadro's number. We won't be using it. It's just going to be constant for the problem that we're going to look at. So I'll just leave it at that for now. If you haven't taken chemistry, then that might not be so familiar to you, but don't worry about that a whole lot right now. R is the ideal gas constant. It's 8.31 joules per mole per Kelvin. We actually won't use this constant much at all either, but it is a good reminder here that we're in SI units with joules and that we're in temperature units of Kelvin if we're using that number. Okay. And then temperature must be in Kelvins here. And that's important to memorize and remember here because we're not going to be using the R very often. So you won't actually get the reminder of seeing that. I might not even write this down because we aren't going to use it. Okay? We're going to be talking about changes in pressure, volume, and temperature. And when we're dealing with changes in pressure, or V or T, and these things are constant, then these will never end up being in our equations. They're always going to drop off. So you'll never be plugging this in and kind of getting the reminder right in front of you that you have the Kelvin in there. So just make sure you remember that with this. This has to be in kelvins, everything else is in SI units, and the pressure has to be the absolute pressure. Make sure you remember to pay attention if you've been given a gauge pressure or not when you're dealing with these pressures here. Okay? So for changes in P, V, T, let's say that we can have P1, V1 is equal to N, R, and T1 for some initial state or final, doesn't matter. And we'll have a P2, V2 is equal to N, R, and T2. These are just two different states, 1 and 2 here, you know what I'm saying? Okay. If we're talking about changes in P, V, or T with our number of moles and the R is always constant, then we're going to approach our problem by just taking these two and putting them together. If I say P1, V1 over T1 is equal to NR, okay, because NR is constant, and I have a P2, V2 over T2 is equal to NR, then we can just take these two, set them equal to get P1, V1 over T1 is equal to P2, V2 over T2. Okay. So to analyze any changes in these variables right here, this is actually going to be a much more convenient formula than just starting over here with the ideal gas law. Okay. We're going to be looking at changes. I'm not going to ask you to find the pressure when the temperature and the volume is something, where you would just use this and you'd find the pressure of that ideal gas. We're going to see how things change due to a temperature, a volume, or a pressure change here. So this is almost the place where I think you should be starting your ideal gas problems, as long as we're talking about changes in the P, the V, or the T. Okay. Now you might remember from chemistry that you probably saw different equations that all had different names. Charles' law, Boyle's law, for things like when temperature is constant or pressure is constant. If temperature is constant, then you have P1, V1 is equal to P2, V2. You guys remember seeing those equations? You don't need to remember those by name. You don't need to remember a separate formula for the case when P is constant or V is constant or T is constant. You can just use this all the time, and if T is constant, those cross off. If V is constant, those drop off, or the same thing happens with the P. So we don't need to think about three separate equations for those three separate cases of constant P, V, or T. Just use this to describe any changes in any of these variables here, and if something's constant, then you'll see that it's just going to drop off. Okay? Some of you remember doing things like that in chemistry? Okay. You also would have done things where you just simply use this, you calculate moles and all that, but we're not doing that here, so really